Hi, my name is CHENG and my matric number is 2926888, and today I'm going to present about the topic ordinary differential equation in my individual assignment. In mathematics, the term ordinary differential equations, also known as ODE, is an equation that contains only one independent variable and one or more of its derivatives with respect to the variables. In other words, the ODE is represented as the relation having one independent variable x, the real dependent variable y, with some of its derivatives, which is y prime, which is the first derivative of y and second derivative of y, and y and with respect to x. And ODE has remarkable application, and it has the ability to predict the world around us, and it used in a variety of disciplines like biology, economics, physics, chemistry, and engineering, and it helps to predict the exponential growth and decay, population, and species growth. The use of ODE are modeling the growth of disease and describe the movement of electricity and describe the motion of the pendulum and waves. Secondly, which is the order of ordinary differential equation. The order of ordinary differential equations is defined to be the order of the highest derivative that occurs in the equation. The general form of n-order ODE is given as fx, y, y prime, and y power of n equals to 0. Note that the y prime can be either dy over dx or dx over dt, and y power of n can be either d power of n y over dx power of n or d power of n y over dt power of n. And n-order ordinary differential equation is linear if it can be written in the form which is AO x y power of n and plus A1 x y power of n minus 1 plus A n x y equals to Rx. The function AJX, which is the j smaller or equal to 0, and n, which is nj, which is more than or equal than n, are called the coefficients of the linear equation. The equation is said that to be homogeneous if Rx equals to 0. If Rx not equal to 0, it is said to be a non-homogeneous equation and also first order differential equation here. The ordinary differential equation is classified into three types, such as autonomous ODE, linear ODE, and nonlinear ODE. For the autonomous ODE, which is a differential equation which does not depend on the variable, say x, is known as an autonomous differential equation. And next, linear ODE, which is if differential equation can be written as a linear combination of a derivative of y, then they are called linear ordinary differential equations. This can be further classified into two types, which is homogeneous linear differential equations and non-homogeneous linear differential equations. And next, nonlinear ODE. Nonlinear ODE, if the differential equation cannot be written in the form of linear combination of the derivatives of y, then it is known as non-linear ordinary differential equations. The law related in ordinary differential equation, which is Newton's law of cooling. Newton's law of cooling is a fundamental law that describes the rate of heat transferred by a body to its surrounding through radiation. This law states that the rate at which the body radiates heat is directly proportional to the difference in the temperature of the body from its surrounding, given that the difference in temperature is low. For example, the higher the difference between the temperature of the body and its surrounding, the more heat is lost, and the lower the temperature, the less heat is lost. Next, I will be talking about the Newton law of cooling formula. The Newton law of cooling formula is a formula for calculating the temperature of a material as it loses heat to its surrounding through radiation. According to Newton's law of cooling, the rate of loss of heat, which is negative dq over dt of the body, is directly proportional to the difference in temperature, which is equal to d2 minus T1 of the body and the surroundings. We can represent it as negative dq over dt equals to k multiplied with the T2 minus T1. So for the k is the proportionality constant. So for solving the above differential equation, we will get, which is Tt equals to Ts plus To minus Ts multiplied with the e power of negative kt. So for the T is the time, and for the Tt is the temperature of the body at time t. So for the Ts is the surrounding temperature, To is the initial temperature of the body, and the K is the proportionality constant. The relation between the drop in temperature of the body and the time is shown using the cooling graph. The slope of this graph shows the rate of fall of the temperature. The cooling curve is the graph that shows the relationship between body temperature and time. The rate of temperature fall is determined by the slope of the tangent to the curve at any point. So the graph below shows the temperature drop and time relations. Next, I will continue with an example of Newton's law of cooling. So for the question 1, the oil is heated to 70 degrees Celsius and it cools to 50 degrees Celsius after 6 minutes. So calculate the time taken by the oil to cool from 50 degrees Celsius to 40 degrees Celsius given the surrounding temperature, which is Ts equals to 25 degrees Celsius. So now I will be talking about the solution for this question. So for the step 1, we know that the temperature of oil after 6 minutes. So for the Tt is equal to 50 degrees Celsius. The surrounding temperature, which is equals to Tx equals to 25 degrees Celsius, and the temperature of oil To equals to 70 degrees Celsius, and time to cool to 50 degrees Celsius equals to 6 minutes. Step 2. So according to Newton's law of cooling, which is Tt equals to Tx plus To minus Ts multiplied with the e power of negative kt, we know that and we will move the Tx to the left hand side, and we will get the Tt minus Tx, and after this we will let the To minus Tx move to the left hand side also, so we will get the Tt minus Tx over To minus Tx equals to e power of negative kt. So therefore we will get the negative kt equals to ln Tt minus Tx over To minus Tx as the equation 1. Next, step 3, we will substitute all the values into the equation 1. So negative kt equals to ln, we will substitute all the values, which is become negative kt equals to ln 50 minus 25 over 70 minus 25. So we will get negative k equals to ln 0.55556 over 6. Therefore, we will get the k equals to 0.09796. So lastly, for the step 4, for the average temperature from 50 degrees Celsius to 40 degrees Celsius is equal to 55 degrees Celsius. So by using Newton's law of cooling, we will know that we will sub the k, which is equals to 0.09796, we will sub into the equation. So we will know that, so it will become negative 0.09796 T equals to ln 45 minus 25 over 70 minus 25. So we will get the negative 0.09796 T equals to ln 0.44444. We will equal to ln 0.44444. And next step, we will move the negative, and it will become 0.81093, and lastly t will be equals to 0.09796 over 0.58778, and lastly t will be equals to 8.278 minutes. So thus the time taken by oil to cool from 50 degrees Celsius to 40 degrees Celsius is 8.278 minutes. So for the conclusion, we can conclude that the ordinary differential equation, which known as ODE, are equations where the derivatives are taken with respect to only one variable. There is only one independent variable. And the ODE is classified into 3 types, which is autonomous ODE, linear ODE, and non-linear ODE. And the law related in ODE is Newton's law of cooling, and so on. And for the ordinary differential equation application in real life are used to calculate the movement or flow of electricity, motion of an object like a pendulum, and to explain the thermodynamics concepts. And in medical terms, they are also used to check the growth of disease in graphical representations. So that's all for my presentation. Thank you.